So to be clear, we are going to do common mistakes on Wednesday. We will round to on Friday. So my apologies for not kind of being ready out of the gate, but I didn't get to look at them until this morning, and then I ran into a bunch of Algebra 1 stuff I had to grade this morning. So, yeah. What's up? Does it have a name on it? Sure.
What?
Miss Jessica Booker? Yeah, just leave it.
Another one of those mini ones? Okay.
All right.
Is this going to be continuation?
No, we're going to do 7.2. All right.
They are all related.
I don't know where her planet is. You can pay her. You can pay her. I think it's the Paris.
I love it. No one's listening to me. All right. I would love to tell it to you, but everyone's talking. So. All right, so we're going to do a number talk in a second. Let me just give you a visual of what we're learning about today, though. So again, we're doing Unit 7, which is all about volume and, well, we did our area 4A, but we're going to be talking about volume from pretty much here on out. Today, what we're going to be doing is what you can see on the board. It's volume by cross-section. So we're going to have an area in the XY plane. Now, that XY plane, you'll notice, has a little bit of perspective on it right now. So let me see if I can drag this guy around. I'm going to be using this graph today. Woo.
I feel like we did this last year. Is this what the circle
That's
is
true.
doing?
Yeah, I did not build this, so you can kind of see that this is going to be the first problem we do today. This is the square root of x on the xy plane. That would be if it was 2D. We're going to draw that, and then we're going to put some cross sections on it. Anyone think they see what shape is being built up out of the paper? It's a square. So we're going to talk about a lot of different shapes today, and I'm going to try to do this graph. It's hard for me to remember where everything is because this has a lot of different things in it. So excuse me while I try to click around for a second. Where's the stupid shape? Sorry, you can change the shape. Oh, there we go. So you can change this to triangles. We have semicircles. I can do an octagon. We're going to be dealing with mostly semicircles, squares, and some different types of triangles today. So when I can, I'll try to show you what this looks like, but I'll also post this link if you want to play around with it. I did not make this because I am not smart enough to make this. I can go into there's thetas in there. But we're going to be taking that and kind of integrating an area formula. Yeah. I have no idea. Where was that? Customization? Nope. Input? It's probably not going to like that. I think it has anything less than 3. It's just the semicircle. So this section is not very difficult. And I know some of the AB, I think anyone coming from one of the AB teachers did not get any of Unit 7 last year. So if this feels new to you, it might be new to you, especially math analysis is definitely new to you. Last year I taught this from scratch in BC and it went really well. So don't worry if you didn't get this last year. It's super repetitive. Again, we're going to be doing a lot where we're like setting up but not evaluating. I really like this unit because in an essence, it is visually stunning. So have a little bit of fun there. All right. My AB class requested that I do the same number talk with you that I did with them because they think that you're not going to get it as fast as I did. It took them a long time though. Are you ready? I'm going to put a number pattern up on the board. If you've seen this before, you can play along, but the goal is don't tell anyone the answer. If you think you have it, you can raise your hand and I will let you guess the next number in the pattern. All right, the first number, what do you think?
Wait, is it that?
What?
Yeah, is it that?
No, what is that?
Fibonacci?
Yeah.
Okay, I was like, Miss Hefty.
Well, no, I did this and then someone was like, is it Fibonacci? I was like, no. What do you think the first number is?
0. Oh, okay.
All right, this is the second number. 3. This is the third number. This is the fourth number.
Is this similar to a
This
series?
is the fifth number. All right, hold on. I'm gonna let you ponder for a second while I pass out the notes. If you think you've got it, I might have shown this to my class last year. So if you think you've got it, you can raise your hand and I'll let you guess the next number.
Got it. Sorry. Oh.
Kirby got it like mid-range. He thought he would get it very quickly. Because you're more mathematical. All right, Nina, you think you have it?
I think so.
Do you want to do the next one then?
3, 1, 2, 2, 1, 1.
Correct.
Let's go.
Let's go. Yeah. All right. Does anyone want to try the next one? Anyone else think they got it? All right, I'll do the next one. Who's writing that? Anyone think they got it?
Yeah.
Yeah?
Yeah.
Okay.
1, 1, 1, 3, 2, 1, 3, 2, 1, 1.
Hey.
Elena?
1, 2, 1, 1, Wait, I think I got it. Okay, it's 1, 3, 2, 1, 1, 3, 1, 1, 1, 2, 3 1s, 1, 3, 1, 1, 2 2s, and 1, 1.
If you were paying attention to how she said it, you probably got it.
Yeah,
Can I-
do it.
1, 1.
You did give it away.
1, 3. 1, 2. 2, 1. 1, 3. 1, 1.
No.
3 1.
Well, like 2.
3 1s.
Well, yeah, I was thinking 1, 1, 1.
Can't do that.
1, 2. 1, 3. 2, 1. 1, 3. 1.
All right, everyone think we got it?
Oh.
Let me reiterate what, well, actually, let me go through this one just later. It's easier. Here, listen to how I say it. 1 1, 1 3, 2 1s, 3 2s, 1 1. Yeah. 3 1s, 1 3, 1 2, 1 1, 1 3, 1 2, 2 1s.
Wait, so how do you start it?
Just with a 1.
So like there's 1 1, and then there's 2 1, and then there's
You say how many of the number are.
1 1, 1 2, and then you say that back.
You say the one above it.
Say it out loud.
Oh.
There's 1 1. How many ones are there? 2 1s. There's 1 2 and 1 1. 1 1, 1 2. Are you ready for a better question?
Yeah.
It's honestly people who are like good at math patterns. I like to consider myself good at math patterns.
I like to think I'm pretty
hard.
good at
Because you want to make it match, and it's not really.
I don't like that. I'm okay.
Will there ever be a four?
No.
Why not?
Because you need to.
What? I'll leave you with something to ponder.
How do you get one? How do you, the one with an arrow, how do you get the second one?
How do I get what?
I'm gonna say yeah.
This is 1-1. I don't think they're 1-3. This is 2-1.
If you're saying 1 or 3.
Look how long it is.
All right, so I'll let you ponder. To address controversy, because my AB class did not like when I started these notes. Yes, I understand this is BC Calculus. Yes, I understand this is not my name anymore. Yes, I have edited my notes since I got married. I just forgot to edit the heading, so apologies. So we're doing volumes by cross section today. This, in essence, is not a very difficult subject. We're going to lean a lot on what we did last class with the top minus bottom situation. And I'm going to be breaking my decisions into a lot of very discrete pieces. So I'm going to break a big problem down into several little problems. What we're going to do, kind of looking at this graph, is I'm going to try to find the area of this cross section, whatever that number may be. Use this one instead. Go away. I hate this keyboard. 4. All right, so the first one we're going to do is this one actually, and we're going to look at this as we go. We're going to be drawing our region in the XY plane. We're going to be finding the area of that cross section, and then to find the volume, we're going to integrate the area of that cross section. So while this is not, hi, we just found your notebook. It's on the shelf. See you tomorrow. All right. While we can do this in terms of X, we can also do this in terms of Y. I'm using different bounds because remember we have to use Y bounds if we're talking in terms of Y. But none of this is super crazy. I'm going to be splitting this into 2 decision-making processes. You're going to notice for a lot of this, I will be finding whatever A of X or A of Y is. So I'm going to be finding an area formula, and then I'm going to be putting it in an integral. Now, there are a ton of different shapes I could use for this. So I could use an octagon. I could use, I don't know, squircle. Who knows? But I'm going to be using probably one of these 5 shapes. These are all the ones I've ever seen on the AP test. I will say the square and the semicircle are the ones that are used most often by far. But the one year that I said it's always a square or a semicircle, it was an isosceles right triangle with a base as a leg, and my students were really mad at me. So I'm going to show you formulas for all of these, but those 2 are going to be the ones you're going to see most often. So in this table, I'm going to draw a picture of the shape, and we're going to find the area of the shape in terms of its base. Now, when I say base, what I mean is the length of the shape that's in the region on the plane. So like this space right here, where I'm in the region with that shape. So not the part that's kind of coming out of our paper, but the part that's stuck to the paper. So would you agree that this is a close approximation of a square? That's really terrible. I'm going to try that again. No, I would not agree. Better? Okay. All right. If this is the base, I'm going to call it B. What's the area of that square? B times B or B squared? Really? All right. I'm going to skip semicircle because it's the hardest one. We're going to come back to it. This is a rectangle. This is base. What's the area of it? B times something, right? Base times height. I'm going to make a note here that this height, whatever it is, you'll get info about. So we're going to see one later today where they're like, oh, the height is 3 times the base. So you'd be able to plug in 3b for that h. So you'll get info for that guy. For the two triangles, I think it's easiest to think of these as proportions of a corresponding square. So let's talk about some of these words because it's been a hot second since we talked about the word isosceles. Anyone know what the word isosceles means? Two sides are the same length, right? So we're going to talk about two different types of right triangle. This one is going to have the base, meaning, sorry, not the base. The base is a leg, meaning not the hypotenuse of the triangle. So here's what that could look like. Here is a right triangle. You know it's right because this is a 90-degree angle. Where I'm claiming this side and this side are both the same size. I notice the one that's the same size is not the hypotenuse. So the one that's on the bottom is not the hypotenuse of that triangle. Now, I could do 1/2 base times height for this triangle, but I would encourage you to think of this as part of a larger square. The one year that this was on the AP test, one of my smartest students, while everyone was complaining that this was the shape, was like, oh, it's just this proportion of a square. How much of the square is it? Half. What? What? Because I graded their papers all year? He was very hardworking, but also was a swimmer and would consistently fall asleep during class, wake up, and know exactly what we were doing. He's a good kid. I think he lives in New York now. I taught his brother too. All right, the right triangle with the base as the hypotenuse. So let me put this long side down here. I like to think of this one as like the flap of an envelope. So here we've got legs are here, right angle here. Notice that long side is the hypotenuse. I need a new one, right? I meant to, and then the Rona. How much of the square does that look like? A 4. You could pop into the room next door and try. Do that? Oh, yeah, because it's Mr. Brown. All right. Now, the last one here, our semicircle, is a little bit weird. And that's because normally, ooh, that's not a good semicircle. You know, writing and talking is really hard. So the problem with the semicircle is we usually don't think of the area of a semicircle in terms of its entire base. What do we normally say is like the area of a semicircle? 1/2 pi r squared or pi over 2r squared is normally what we would think of. So if the entire bottom is the base, how much is the actual radius? Let me ask the question differently. If this entire bottom is measured b, how much is just the radius? 1/2 b or b over 2. So some people like to set it all up like that. I actually, a few years ago, I think when I was teaching, decided to simplify that. My brain has a little bit of room for memorization. If yours does not, you're more than welcome to think it out. But if you square this 2 on the bottom and multiply it by the other 2, you can get a nice formula of pi over 8b squared to get that area formula in terms of the entire base instead of in terms of the radius. I found that really useful because semicircles come up quite a bit with cross sections. So if you have a little sliver of your brain for that formula to kind of memorize as a formula, kind of worth it. So I'll be using that kind of like a formula today of area of a semicircle, essentially in terms of the diameter of it. All right, now that we've got all of our shapes, let's actually do this question. I think we're gonna integrate 2 of these by hand today, and then we're gonna not. Maybe not even 2. That was a big sigh for not even being a whole problem into the question. There you go. All right, so we're gonna do, this is actually literally the question that I showed you at the beginning on the Desmos graph. So we're looking at this guy right here. We're gonna draw this graph because this is the graph. The red line is the square root of x. We're cutting it off at x equals 9, and we're cutting the bottom at that x-axis, which is y equals 0. So let's kind of read the question and see how they're getting that region, and then how they're knowing which way to orient their squares, that their squares, all of that stuff. These questions are pretty straightforward as far as what you're going to do. So we have, we want to find the volume of the solid whose base is this region. Notice the word again, bounded. We're talking about surrounded by these curves. So you're thinking of these curves like a fence. The square root of x looks like this guy. And I'm going to drop a vertical at the vertical line x equals 9. That point is 9 comma what? What would the y value of that point be? Doesn't look like 0. 9 comma. Oh, okay. 3. Square root of 9 is 3. 0, 0 is this point, if that's the one you're talking about. What would another point on this graph be, just for fun? 4, 2 would be a great point. 1, 1 would be another great point. 7, the square root of 7. Really. All right, so we've got that line above, vertical line to the right, and the x-axis below. So we're talking this like, what does that look like? A quarter of an ellipse guy there. All right, we're going to be doing cross sections that are perpendicular to the x-axis. Now, when you see this phrase, perpendicular to the whatever axis, you want to pay attention to this letter. Not only is it going to tell you how you're orienting your kind of stuff as you're going through, but this means we get to use x as our variable. Cross sections are nice that way. They kind of tell us exactly what to do. So we're going to be in terms of x. Now, there are a couple of things that I like to draw on my paper. One of them I'm going to kind of make non-negotiable for you. We're going to be very concerned with the base of our shape. So what I want you to at least do is draw anywhere in your region one vertical line, here vertical because we're perpendicular to the x-axis, within your region. It can be anywhere in your region. So I could draw it over here, whatever you want, but at least that vertical line to represent the base of your shape. Now, I often like to draw kind of a perspective version of my shape, but it has made a lot of students mad in the past. So I'm going to draw it now. If you hate it, don't do it. If you do like it, you can do it. If you want to do it a different way, do it a different way. So I'm going to attempt to draw a square with perspective. You can, everyone, I've been yelled at so many years for doing this. So I'm imagining my square is coming straight out of my paper. If you like it, great. If you hate it, at least draw the vertical line. If you do a little bit of shading, I like that. All right, so pretty much non-negotiable is just this line right here. You like it? Thank you. All right. Now, I will tell you, this unit, when I first learned calculus, this unit was a lot for my little brain to handle. I am not the best at spatial awareness, so I do a lot of things to separate my decisions into very small decisions that I have to make one at a time. So one thing I found useful is to split the decision between area and volume. What I mean by that is I'm going to start by writing just the area formula for this square, whatever I'm seeing. So let's start. I know it's a square because it tells me it's a square. What is the area formula in terms of my base, like out of that chart that we had for the square? B squared. All right. Now I have to figure out what B is. This should feel extremely familiar to how we did the top minus bottom area from when we learned 7.1. What is our top function up here? What's the square root of x? And what is our bottom function down here? Yeah, it's the x-axis or y equals 0. You're going to see me throughout the unit doing a lot of subtracting 0 to remind myself to subtract. If you want to just do the square root of x, that's fine. I'm going to simplify this. This is the square root of x quantity squared. That's x. Now, a good place to sanity check, that means the area of this square is going to change depending on the x value. That makes sense. If I drag, hold on, I can actually see that on the Desmos graph. If I drag this square back and forth, you should see the size of it change. Where is my square? This guy. Whee. So you can see his size change. Also, if you think of that function as x, the smaller x gets, so over here, the smaller the square gets. The bigger x gets, the bigger the square gets. So you can kind of do a little bit of sanity checking at different points during this process. Now, after we find the area, to find the volume, we're going to integrate. You can kind of think of integrating as like adding a dimension. So we're going from 2 dimensions to 3 by integrating. All right, I'm going to stick my differential, that dx, on the end. And what's kind of glaringly missing here? Bounds. Anyone got an idea of what the bounds should be? Good. I like that you said 0 to 9 and not 0 to 3. The bounds of integration should match the letter that's in my problem, my variable in my problem. If you ever get stuck, a good trick is to take your pen and kind of put it on your B and try to slide back and forth in your region. I can slide to the left to 0 all the way to the right to 9. All right, just for giggles, let's actually do this one. What is the antiderivative of x? All right, I've got my from 0 to 9. I'll plug, which bound goes in first? Cool. Please stop plugging the wrong bound in first. So I get 81 over 2, which is slightly north of 40. I gave us a decimal here mostly just so we can sanity check our answer. Things I like about this answer: 1, it's positive. We're talking about volume here, just like we talked about actual area last time. If we get a negative answer, we've done something wrong. Especially since our base is always going to be squared, we should be getting a positive number no matter what. Also, the relative size of this seems okay. We're going to get slightly bigger numbers because we're talking 3 dimensions, so the volume is going to get a little bigger than we would expect. But going from 0 to 9 and kind of up a bit, this should be a relatively big number. Michaela, did you have a question?
I feel like we're against it, but like
Okay.
the square root of x,
Yeah.
you got that from like the y and the square root of x, and so you got the 0, but that's just like the x coordinate for the.
So that is like this y equals 0 as my bottom function. So since I was going down to just that horizontal y equals 0, that's where that bottom function is coming from. We're going to see sometimes it'll be a different function. We're actually going to see in the next example, it'll be like an actual curvy function. But here we were just going down the x-axis. All right, everyone cool and comfy? All right, I want to do one more set of questions, and I want you to pull out your pattern-making brains, and after that, we're going to take a break. So with this set of notes, and the set of notes that we're going to do next time as well, what I like to do is take the same region and do different things to it. So what I want you to figure out right now, it's going to become immediately apparent pretty darn fast, is I'm going to take this region that we're going to draw in a second, and we are going to see what happens when we change the shape. So what's going to happen if we just straight up change the shape as we move through? Let's get a graph going. See if I can figure this out. All right, so we're going to keep the square root of x. We're going to change to x squared. And I got to change my bounds quite a bit because there's a whole lot of junk going on. So I think the area that I'm looking at, it says bounded by those 2 regions. Everyone see this kind of tiny leafy boy in here? That's what I want. I want that in there. So it looks like they intersect at 0. Where is this point? Where do they intersect again? Where is the square root of x equal to x squared? 1, 1. So I'm going to change this b to 1. And I'm going to zoom in a little bit. Okay? So what I'm going to try to do is graph this. Now, when I graph it, I know it's going between 0, 0, and 1, 1, and that's it. So I'm going to try to blow that up a little bit so I can see it. We got this guy. I got this guy. Is there exciting stuff happening in the hallway? Always. Did anything exciting happen last week while I was gone?
There was a fight and Mr. Patton.
Okay, wait, that was last week.
Oh my god!
That was 2 weekends ago.
Yeah, and then there was Wednesday last week.
Yeah.
Oh my god!
Someone had to. It was so bad.
No.
Oh no!
I was
Yeah.
I thought it was 2 weeks ago.
It was.
I remember I went to the gym.
All right, so non-negotiable line we're going to draw. We're going to pick anywhere in our region, and we're just going to draw one vertical line. I know I'm drawing that line as vertical because I say perpendicular to the x-axis. I am happy to see that because that means that all my integrals are going to have the letter x in them. That's usually a little bit easier to do. All right. Let's do some squares. All right, I'm going to start. If you want, you can draw your little square in. Little square boy. I've been drawing them for a while. My mom was an art major, well, for a while, and then she switched to math. Classic. She's actually really good, but I'm not artistic. All right, what's the area of a square? All right, let's talk about B. All right, again, theme. Top function minus bottom function. Oh, we didn't label them yet. Anyone know what that top function is, which one it is? Square root of x. And bottom function, x squared. So I'm going to do the square root of x minus x squared. Now, I just talked about this with my AD class as well. Am I allowed to just call that x minus x to the 4th? No, please stop doing that. Yeah, you'd have to like write it out twice and like FOIL it. We're probably not going to do that. These get really big really fast, so that's why there's going to be a lot of setup, but do not evaluate or evaluate on your calculator. This, we're just going to set it up and not evaluate. Rashad. It did not. That would be actually very problematic for this graph because your square root of x is not defined on negative numbers. We wouldn't choose that. We want the bounded by, so think of them again like a fence. So you want the part that's fenced in, but yes. So we need both of those graphs there. If we didn't have one graph, we'd have like infinitely long squares, which would be problematic. All right. So I am again going to shove this inside my volume formula. If you're sitting here like Hefty, why are you doing that in 2 different steps? I don't need 2 different steps to do this. Like, you do you. I could probably do it without 2 different steps. I just like to do one decision at a time. So that's why I'm doing it in 2 different steps. Glaringly missing. Bounds. Thoughts on them? All right, question, because we got a bunch of 0 to 1s. Is that this 0 to 1 or this 0 to 1? X. Yeah, I like that Nina saying X. All right, if I integrated this, I'd get a cool number. So technically I'm not following directions here. We're going to set up but do not evaluate. Technically, you're right. Actually, I should be finding it. So when I see find, this should mean my answer is a number. I'm just being lazy.
But like, if we were on a test and we had this, would we do that?
If I put this specific question on the test, I would probably either give you a calculator or you would have the directions set up but do not evaluate, because that's a nasty integral. You'd have to FOIL that out. You'd have fractional exponents. It would not be a good time. So you'd most likely either have a calculator or I'd say just like set it up and leave it. All right, semicircles. Let's look back at our picture. So here's our squares. Let's see if I can go in a little more. So we got our squares. Should I put more squares in there? Hold on. Is it this one? All right, more squares. And let's say I make the shape a semicircle instead. Do you think the resulting volume will be bigger or smaller? Squares, semicircle. Square. Sorry, do you think the semicircles will be bigger or smaller? What? 100? Sure. Yeah. It's not a trick question. Where's my perspective, boy? They put the dot too far out. What perspective would you like? All right, so there's the squares. Actually, this is a good idea, Rashad. There's the squares, and where did the semicircles go?
Right there.
Ah.
No, but look right.
All right, so look at this.
I think.
Which one's bigger?
So more of the shape, because more of the squares get cut off.
What do you mean more of the squares get cut off?
Like only a smaller amount of the squares in the round.
Remember, there's going to be infinitely many squares, though.
That's probably
No, I mean like.
All right,
one single square.
you guys are in the back are getting mad, right? Which shape itself? Even if I just had one of them, which shape looks bigger?
Square.
The squares. So the squares one should be bigger because theoretically, let me show you. Theoretically, these are going to fill out. So I'm going to get something. This one will be a little different, but I'm going to get a solid shape. So this one has a square, but I'm going to get like a solid shape out of this. So it doesn't matter how many squares, because there's infinitely many squares. I got a solid thing. So I agree. It looks like the squares are taller than the semicircles, no matter where I'm putting them. So theoretically, the square's volume should be bigger than the semicircle volume. Let's see how that works. This is a Word document. That's not what I wanted. All right. Can I get a different color? Blue. Let's do it. All right. So from what it looked like the semicircles were doing something more like that. All right. Now, does anyone remember the area formula we made for the semicircle? Pi over 8b squared. Now you can certainly do pi over 2 and then b over 2. I'm just going to take a second to simplify that all from the outright, so I can do pi over 8.
Wait, what happened?
So this b, we put in b over 2,
Oh, right. The other two was the R.
and then we simplified for that front fraction. All right. Now, my base, looking at the base in the picture, is that b going to change from the squares b at all? Or is it the same functions top, same functions bottom? All right, so I've got pi over 8. Do you think changing the shape will ever change that base? All right. If we do this, I'm going to shove, we're kind of trying to figure that out, so we'll keep talking about it. I'm going to shove this area formula in here. Again, notice it's really gross. We mostly just made it a little bit grosser by adding a constant out front. Yeah, bound's still 0 to 1? Still this 0 to 1? Okay. So literally, only thing that changed, let's look at it, is this number right here, right? Question, is that number bigger or less than 1? Less than. So would you agree that this volume is less than that volume? Makes sense. That's what it should have looked like. All right, let's quickly go through the rest of these because they're not going to be that interesting now. Yes. Mm-hmm. So if you thought out the original one, if you didn't want to use the pi over 8, if that's what you're talking about, you would kind of be thinking, you'd be thinking of like pi halves for the semicircle. You'd take the base, which is x squared of x minus x squared, put it all over 2 and square it, because you need the base over 2. So it's easy to think out. It's just a little bit nastier. So if you're thinking plugging into a calculator, if you have enough space, I think it's worth it. All right, let's do these last two really quick. If we're talking rectangle with 1/2 the base is the height. So essentially I'm taking this guy and I'm making him kind of shorter. Or if you take that guy here, we're making him shorter like that. Area formula, let's see. Rectangles is like base times height, right? Oh, but we know what the height is. Okay. So base times 1/2 the base. So yeah. So if you thought about this as like, it's take the square but cut it in half, you could also think of it that way. B squared over 2, whatever you want. Yeah. So it's kind of like I'm taking that square and cutting it vertically in half. Now, I know I didn't write it down. Do you think the base is going to change? Top minus bottom for those functions?
No.
I don't think so either. So I think the volume is going to be, let's see, I'm going to put that 1/2. I'm going to have my b squared, which I think is still square root of x minus x squared. Do you think the bounds are going to change? No, still 0 to 1.
Yeah.
I'll talk about that in a second. Let's do one more, and I kind of want to show you. So isosceles right triangle, the base is the leg, without turning to the front page. Anyone know if it's the half or the quarter? Good. All right. If we're talking about that as a proportion of the square, you're talking like this triangle right here. I can't show you that actual one because this does an equilateral triangle. Yeah, so imagine that top point is kind of pulled over to one side. You guys think the base is going to change? Do you think the bounds are going to change? Anyone notice anything interesting? Does anyone notice it's the same as the volume formula we did for number 3 with the rectangles? Now, if I look at both of those, let's say I was able to graph both of those in Desmos, would those look like the same object? No, they would definitely not, but they would have the same volume. So kind of an interesting scenario. Now, Hannah asked a really good question, like, is it always going to be like this? So normally you're going to be asked to do one region in the plane with one shape. So what I wanted to illustrate here is mostly that the shape doesn't really cause too much of an issue. That's not the big decision-making process. That's really giving you a constant. The big decision-making process has all to do with that region. So spend more time than you think you should working out what does that region look like? Do I have the right thing that's bounded? And especially, do I know the right top minus bottom? You may be saying, why does subtracting the right way matter? I'm squaring it. Correct for now, but we're going to have a different method for rotating later on where the top minus bottom will definitely matter. All right, someone had a hand. Julian, did you have a hand up?
Oh, no, I got it.
Cool. All right, any questions or are we ready for a break? Break. All right, take 4. It's a lot of noise.
Remember when you were standing for right?
There's a big sigh. Same.
Can I have more work after this?
See, that's one of the bathrooms. What's in it? What is it? Was it about the tutoring? Oh. Did you scan it? I'm about to.
Yeah, let us know what.
Are they, yeah, we're like, are they gonna like do my homework for me?
Please.
I hope so.
The mobile game.
Nate. I wouldn't worry about it. If I hear anything like that, you know. Sometimes they change their mind. Oh, I'm so tired. That one?
The small one.
Oh.
It's like a quiz. It's a Google box.
For what?
You got a symptom checker.
Ew.
Can you just look at it?
No plans.
I
Okay.
should call my.
What's your plans next?
Please don't. Oh. Just confirming that you're like doing okay every night.
If needed.
It's nice to have a little positive reinforcement at the start of your day.
Y'all try to get another early release. Turn it on bathroom light. Yeah. Did the timer go off already?
No.
Oh. Let's go.
They were correct.
Wow, they didn't put
Bro.
zeros on it. 9:14, where are you? In my car. Sitting in my car.
I don't know. I'm ready to go to sleep.
What? Yeah, I haven't. What's your urge tonight?
Are we ever gonna do a wellness Wednesday? Have we done one yet?
No, it's supposed to be here. We were supposed to have one, but then they canceled it.
So they keep canceling things because they're like planned as the same week as other things.
You know, I've already planned it too long.
Yeah, because I think I'm supposed to do like Sporkle trivia. Oh, no. Oh, in the last 40 seconds, you may want to grab a calculator.
What? Oh, yeah. Sorry, I did not figure out how to say that.
All right. So we have a couple of goals between now and the end of class. I can get rid of, I didn't ask Word to open. You ever click Word when you didn't mean to and you're like,
No, because our
That's
computer, our
probably
computer's
why
not
they're
on
on
class
the
today, Miss Esty.
I think I just opened it once and then I was just like, stop.
Oh,
All right.
yeah.
So, goals for the rest of class. Goal number 1, how do we do this if we're working in terms of why? How do we know that we need to work in terms of why and what needs to change? You're noticing I'm doing some different shapes here. We're going to go through these pretty quickly because we kind of realize the shape doesn't do too much in this problem. Then we're going to roll to some recent AP test questions. This first one, you'll probably recognize these, well, maybe you'll recognize these graphs. They were on the 7.1. Yeah, they were from the last notes, so we found that intersection point. We're going to remind ourselves how to do that today. Julian, what's up?
Wasn't there a question I figured out?
I don't know.
I thought that there was like something where it's like if it's the same, like different shapes. And you were like, hold on, we're trying to figure that out
Oh.
right now.
I did say that. I don't remember why. If anyone remembers what we're talking about, let me know. I know. If I figure it out, my brain's working in the background on that one. We are also going to, this is probably one of the nastiest versions of this I've ever seen. It was on a multiple choice that was recently released from the AP exam. I can't remember if it was an actual exam or just some practice questions. It's a good one, so we'll end with that one because it's kind of the nastiest. It's a good lesson in like what looks like a gross question isn't necessarily a gross question if you take it step by step. So we've only got 3 questions really left to do because this one, the shape is just going to kind of dictate the area formula we're working with. So I want to notice that this region that we're bounding is exactly the same region we've been looking at before. But again, at the start of this, I want to graph the region. If you ask me for help on a problem set, if I make one, a quiz on this, if we have one, a test on this, if we do it, and you don't have the region drawn, I'm not helping you until you have the region drawn. You got to be able to see what region you're working with. So we're still working with the square root of x. That's this guy. We're still working with x equals 9. Your brain may be saying to yourself, what kinds of graphs will I need to be able to graph? I would say like x squared, square root of x, those kinds of graphs you should be able to graph just from your noggin. Some of the other ones that we'll be working with might be ones that you might have to graph on a calculator. So like anything crazy like this, we're going to be able to have a calculator to use. I'm going to label this 3 again. And we're going to find the different part of this question that makes us working in terms of y. Does anyone see the difference? Perpendicular to the y-axis. Again, for cross sections, it's actually kind of easy because they tell you right out what letter you want to use. That's going to get a little bit more complicated when we start rotating things next class. It's going to become kind of a more complicated choice there. But this guy right here is telling me I'm in terms of y. Graphically, what that looks like is we're going to be perpendicular to that vertical axis. So the line, that non-negotiable line I'm going to be drawing, is going to go horizontally, which is definitely a little bit different. So it's going to adjust what types of tops and bottoms I'm talking about. But the shape, again, is not going to change too much. So let's quickly roll through these. Really, after the first one, most of our work is going to be done. Also, again, to go back to, I forget whose question it was, I think Hannah's. Normally, you'll just have to do one shape. I'm just doing multiple shapes to illustrate right now that it's not changing very much. And to review some of our area formulas. So area formulas. Let's talk about squares. B squared. All right, now, we need to talk about top minus bottom because we're talking about lefts and rights now. Could you point to the side of the room with accordance to this graph that you think top is? Yes, so this side, we're talking bigger x values are to the right. If you need to, you can label top. I like to do that, usually with some air quotes. You could just label top without quotes. Or you can think right minus left, big minus small works well as well. But you want to make sure that your base is a positive value. If you subtract in the wrong way, your base is negative. We're measuring length. That's weird. All right, what does the top function look like? 9. It's this vertical line, 9. All right, what does the bottom function look like? All right. So I hear two things. They're kind of both right, but one of them's more right than the other. So this is y equals the square root of x. But Emery, what are you telling me? All right. I need my integral to be in terms of y. So I'm going to change that to be y squared. Anytime we're going horizontally, we should be working in terms of y. Y should be the letter in my integral. That will probably get highlighted on a test. You may even write a note to yourself that says in terms of y and then put your x in your integral, like a dweeb. Yeah. So think of, here's a couple ways to explain it. I'll explain it until I think you get it. You want to think this base needs to be a positive distance. So one way to think of it is to take the bigger value of x minus the smaller value of x. Now this value of x turns out to be a number. This value of x is changing based on where I do my base. So that's why I have a function for it. But you're talking about the bigger version minus the smaller version. So right minus left, top minus bottom. All right. Let's go to a volume formula. So adding an integral to add a dimension to this guy. This is one that's kind of borderline. I could ask you to do it by hand because squaring that out wouldn't be quite as nasty as some of the other ones. But you would have to square it out to be able to do this integral. What is left? What's my last decision? Bounds. Thoughts on them? Good. 0 to 3. Notice you can still stick your pen on that base and slide this time up and down. You can go as far down as 0, as far up as 3. All right. Let's see if you're paying attention. What changes if I change to semicircle? Just the constant. Let's pop all the way to volume. So bounds are still going to be 0 to 3. Base is still going to be 9 minus y squared. Now it's dy to match that letter. What constant that Nate's talking about will go there? Pi over 8. Because we're talking area formula. Pi over 8 b squared. All right. Let's talk rectangles again. Here, very similar to the rectangles we did before, but I'm kind of saying it more in words. So it says rectangles with height equal to 3 times the base. Could anyone translate this into an equation? Height equals h equals 3b. So if I'm talking area formula, I have base times height or base times 3b. Do you want a notes check before you leave now? All right, so 3b squared. So really, same integral, same bounds. We just got a 3 there. All right, last one. We've got an isosceles right triangle with the base as the hypotenuse. Without looking at your front paper. 1/4. That's our envelope guy. So here's your square, here's your triangle. So literally same integral. By the way, you could put the 1/4 out in front of the integral if you want. My second block got really angry that I wasn't putting my constants out front. You do you. It wouldn't necessarily have to be. That's a really good question. So let's say in number 7, instead of saying height equal to 3 times the base, I could just say like height always equal to 3. So you could have like just base times 3. It'd be a weird shape because it would just be like a constant height, but it is a possibility. All right, let's go ahead. Yeah. No, don't be sorry. So it was both because we were using the leg and because of the specific way the height was related to the base here. So here we had 1/2 base was the height. And since this 1/2 is the constant for your triangle, it just happened to be that way. Okay. All right, so let's go and kind of do some AP style questions on this before we kind of finish up for today. So we're going to work with this region again. We're going to remind ourselves how to find this intersection point, and we're going to do some cross sections. So while I'm labeling this as A, can you read the paragraph or paragraphs, I guess? And in this section, there's like some very, very necessary words. When you find those necessary words, let me know what words you think are necessary. I'll give you a sec. Okay, perpendicular to the x-axis, that's important. Squares. All right, volume, that's going to help us because we need to know whether we're doing area or volume. That's good, we did area last time. I would say there's one more thing that's really important. Region S. We are actually only dealing with S here and not with R. So we only have to deal with one of them. So remember, like I said last time, this was part of a full free response question. So the question we did last time where we found the area was the first part of our problem, and this was part B. I think C had you doing rotation. So the first thing we would do if we were on the actual AP test is we would right away stick f of x in y1 and g of x in y2. I'm going to go and do that, but I think mine are already in there. Could you take a second to make sure f of x is in y1 and g of x is in y2? Also go to your graph, and I would just make sure that you can see the intersection point that we're going to find in a second. Yeah, if yours already has it, great. I just know Mr. Brown's students use these calculators as well. When do we go till today? 35. 35? What? So we're trying to find that, but cross sections built up on it. So not just the area. All right, everyone cool if their functions are in their calculator? Waiting. Yeah, I just hit graph. All right, speaking of, we are going to hit graph because my first task, I know we stored it last time, but just in case we didn't store it or we want to restore it in practice, I'm going to find that intersection point, and in a second, I'm going to write that number down on my paper, label it as A, and I'm going to label it as A in my calculator. That's weird. Are both of your equal signs turned on?
I think so.
If you go over and like press equals, so it's not highlighted, it'll only graph one of the functions. Yeah, it can be really helpful if you're like trying to graph a derivative. You can keep the original function there just turned off. All right.
Zoom it out again.
I would press zoom 6 just to get standard. All right, we cool right now?
Yeah.
All right. Can you remind me how to get the intersection? Where do I go? Second calc or second trace. That's getting to this calc menu. So the blue button and then trace. We want intersection, which is number 5. I like to just literally press the number 5. You can scroll down and press enter though. It's going to ask you 3 questions. You can kind of ignore the first 2 as long as you only have 2 functions because it's just asking which functions to use. When it prompts for the guess, you either need to click a number that's close to that intersection. So you can press 1 enter for this one, or you can scroll until you're closer to that than any other intersection and press enter. So first curve, second curve, you only have 2 curves in there, so you can just literally enter. So usually the only question you're going to have to answer is guess. If there's only one intersection point, you can enter. All right, so remember this number, our 1.0328319. Hopefully.
So I got 1.06. That's what I got.
I got 1.032. I got that one.
I have the right number. I know I do. So if you don't have the right number, I'm gonna need you to go back to your y1, y2, and make sure you plugged in your functions correctly.
Is it just the way you're like scrolling on the calculator?
All right, so I'm not scrolling to get it. Make sure, if you're scrolling around to get it, make sure you're going to second, trace, intersection. First curve, second curve, and then press enter to get. And then it's going to give you a different number. Okay, Nina, you good?
You just press enter, enter,
Mhm.
enter. When they're on.
Enter, enter, and make sure you're closest, then enter.
Enter, enter. Now it says guess again. Oh, intersection. Oh, I got it.
Okay, cool. All right, so I'm gonna label this on my paper. So what was it? 1.0.
1.03.
I want all of it. 1.038319.
Mine says 6.1.
All right, so I've got it on my paper. Why do I want to label it on my paper? I don't want to write that number more than once. So now that I've labeled it A, I can use A in any of the integrals I do on my paper. I want to label it in my calculator. I'm going to go back to the home screen by pressing second quit. I'm going to say, hey, take that X value. I want you to store it, stow, as alpha A. Stow is right above on. I'll do it again. So take that X you had, stow, right above on, alpha A. Why would I want to do that? Because X is going to change if I use X in an integral, so I can't use that. But I don't want to type this number over and over again. So I'm going to tell my calculator, hey, put this number that I have, put it in A, and only change it if I tell you to. Victoria. Oh, did you do it right after you did your intersection? Okay, try to make sure you can't do anything between your intersection and storing it. So it has to be an immediate, yeah. You could call it B or C or whatever you want. Yeah. All right, so let's talk about the question that we're doing. We're doing some cross sections in X. So I've got my vertical line. If you want, I think it's a little too complicated to draw my square here, so I'm just going to do the vertical line. What? What? No. Yeah, so I should probably not call this A. All right. So we're going to find our area. What is our shape? Square area formula? B squared. All right. Anyone remember which function is which? All right. F of X is on the top. We can check on our calculator or we can check with our knowledge of functions. I would probably check on my calculator here. Sorry, I forgot my equal sign. All right. So I have F of X minus G of X all squared. If I'm now doing my volume, I'm going to steal that area. Again, if you think you can do this in one step, by all means. It is two very discrete decisions, really just the area formula and the bounds. Next class gets them more complicated with the decisions. So, thoughts on the bounds? A to what? Is it 2 or is it 4?
It's 2.
Why is it 2? We're doing X bounds, so we do want 2. All right, let's make sure we can all plug this into the calculator. So I'm gonna plug this into mine. We're gonna see if we all get the same number. How do I get an integral? Cool. Math 9. I'm gonna put my A in there that I've stored. I'm gonna go to 2. I'm gonna open some parentheses. And I don't feel like typing out F of X and G of X. And then I remember. I have them in Y1 and Y2. Anyone remember how to get them? Alpha, trace.
Our Y1 was that.
technically it doesn't matter here since you're squaring it, but Nazi, I like that you're paying attention because one of the methods we're going to do later on, the order will definitely matter. If it helps, you can label them on your paper which one you put in Y1 and Y2.
How'd you get Y1?
Alpha traits.
Oh, crap.
Why'd you say all crap?
I forgot to square it.
Yes. So forgetting to square it, a very common calculator mistake. You should be getting somewhere north of 1.2. 1.283 to be exact. Things I like about that, positive value. Also, when I looked at the graph, that region looked pretty small. So thinking even with cross sections, my answer is probably going to be pretty small. I feel like that's a good answer. Again, 3 decimal places necessary. So I'm going to say 1.283. Back to someone's question from my lady's table earlier. Direction words that made me know I needed to actually evaluate. This says find the volume versus set up, but do not evaluate. So if the word find is there, my answer should be a number. Ma'am. No, I didn't give you any units, so you don't necessarily, you're not required to give any. They would be some sort of cubic distance units, like meters cubed, feet cubed, units cubed, but you won't need to put any. All right, let's just do this last question. We might not even have enough time for the nose check, but it's a short one. So, but I really like this multiple choice because it looks absolutely disgusting. But if you follow the steps of the problem, it's really not that bad. So this is a good, like, trust yourself question and trust that you know the methods you have to do, even if it looks terrifying. I think one particular thing is super scary about this. What freaks you out most about this question? All right, the graph maybe. Does anyone else? Yeah, when I look at this creeps me out a whole heck of a lot. One, because there's X and Y on the same side. And also, I'm thinking I need a top function and a bottom function. That's one thing. So I need to find a way to somehow like do top minus bottom with the same graph. Yeah, neat. That'd be a great place to start. Let's make sure we know what letter to get by itself. Which way are we doing our bases? Are we doing it perpendicular to the x-axis or the y-axis? X-axis. So do you guys like Nate's idea of solving for y? So I'll have y equals stuff with x's in it. Yes. So I'm going to draw that one random base in. And I'm hoping somehow that I kind of get 2 functions out when I'm solving. It may become obvious quicker to some of you than others how we're going to get 2 functions out while solving. Hopefully, it will become obvious to all of us. Now, I do not have high hopes for what this function is going to look like, so I'm just going to kind of do stuff and hope for the best. I'm going to start by subtracting the x part. I'm sorry. Thank you. Thank you for correcting me quickly. I just really wanted it to be a circle formula, and it's definitely not. Squircle. That's what they call. Has anyone ever been to Lovettsville? They have like a town square, but it's like rounded, so it's a squircle. My friend lives on the squircle. All right, I'm gonna multiply by 81. Personally, for me, I don't want to add any more like parentheses, so I'm just gonna distribute that 81 into both of these things. And then, how do I get rid of to the 4th power? 4th rooted. All right. What should pop up if I 4th root something? Plus or minus. That makes me actually very happy. Let me explain why. That's how I get the 2 functions. This top guy is going to be our positive root, excuse the bad notation, but this bottom guy is going to be the negative root. So that's how we're getting that kind of top minus bottom situation. How are they different? One's positive and one's... So I'm claiming one of them is like this guy. And one of them.
Okay, so you're breaking it up.
Yes, because think of like you have positive y values and negative y values. All right. Did anyone happen to see what shape they want us to use? A semicircle. Should we just set up the whole volume all at once? All right, let's do it. So I'm gonna put my area inside here. Semicircle. Tell me about it. B squared. I'm going dx because you guys said x-axis. What is the top function? The positive root. I'm just gonna write it out. Okay. What's the bottom function? So minus negative. Good. Okay. Anything else? Ooh, bounds. Oh, they didn't tell me anything. Thoughts? All right, let's see. Nina's claim -2 to +2. You like it? If I take my base and I roll back and forth, does it look like they've definitely labeled them -2 and +2? You can also note, see that 16 in the bottom? If you think of like the radius in like a circle formula, how it's like the radius squared, those are like the major and minor axis, but here it's to the fourth. So that 16 is 2 to the fourth. That's technically how you know. But we can trust the picture here. Now, I just want to make one more comment, and then I'm going to see how far you guys can get on this notes check. This on the whatever format this was a multiple choice question, so I did have to plug this into the calculator. One thing you could do, what could you do to the innards of this? So I can't do square root, I can't change the root, but I have one of these technically plus another one. So how many of them do I have? I have, not that squared, I have 2 of them. So if I were plugging this into the calculator, I would personally take advantage of that. So I would eliminate maybe a typo here or there. Now, if you're more comfortable with typing than you are with simplifying, by all means, do whatever is going to make you the happiest. But I know for a fact that I would probably typo something in there. So you can always look for ways to simplify. You could even like square that 2, make it pi/2, whatever you want. What? You could put them in y1 and y2 and reference them as that. So yeah, you could like put that guy in y1 and even do like that minus negative that if you wanted to. There's a lot of clever ways you could get around on the calculator. Oh yeah, you could square the 2. You could square the 2 and then make that a square root if you wanted to. That's smart. Even easier to plug in the calculator. All right, so that's about as hard as it gets for cross section. These really aren't too bad. Next class, what we're going to be doing, let's see if I can find it, is we're going to start rotating. Rotating is a little bit more complicated, but technically a cross section. So I'm gonna rotate this. So pretty. Where's my perspective, boy? What shape do you see?
Flower. It's a circle.
It's so like your cross section. Your cross section is technically a circle, right? Now I can change this a little bit. Hold. So I can make a hole in the middle of it. So we're gonna sometimes deal with discs. We're gonna sometimes deal with washers, meaning it's gonna have a hole in the middle, but the hole is also a circle. So remind me, area of a circle? Pi r squared. We're gonna be dealing with a ton of pi r squared. But we're going to do things like move the axis of rotation. We're going to do a lot of stuff. Don't worry. This was a challenge for me when I learned it. So I have a lot of ways to kind of put our mind around it. So it won't be too bad, but it definitely will be a little spatially weird. When's the hard unit? Depends on what you consider hard.
Well, like the one that you say everything they put.
Taylor series?
Yes.
9. 8 is long.
And
And 9 is. All right, I want to 10 to get this done. You can use your calculator. First one is area. So first one just top minus bottom. Don't do anything like this. Wait, how much do we have?
3 minutes.
Oh, I lied. We're not gonna do this. For some reason, I was thinking 38. Yeah. So you could theoretically, bathroom, go. You could theoretically, like, if you were looking to find the volume of something that didn't necessarily have, like, a clean edge on it. Yeah. So let's say maybe you're, like, trying to 3D print, like maybe a banister for a stair case or something, and you want to know like how much material. Theoretically, you either have like an equation for what that cross section would look like, or like you could model one, and you could kind of
That's why it's not like a different shape.
you could. I have a project when I student project, a huge project. So I had to find anything that was like circular cross section, and you like modeled what the curve would be, and then rotate it back and find it all. That's pretty cool. I'm sure there's other ways that are mathematically simpler to do. I just like this unit because
Because we just like use stuff, and I want to think about like when people like use it.
now, if you ask me that question in Unit 8, I will not have an answer for you. Unit 8 is just so fun though. I'm so excited. It's my favorite.